Mathematics is beautiful because it gives us a way to describe things that are always changing, things such as motion, growth, and speed. Now, if you want to understand calculus, the first idea you really need to understand is the derivative. And in this video, we're going to build up that idea by introducing the formal definition of a derivative, but we're going to do it by building up intuition behind it. Now, to start with, we must begin with the basics. What exactly is a function? A function is like a machine. You give it an input and it gives you an output. For example, imagine a machine that doubles any number that you give it. If I put in the number 1, it'll give me back the number 2. If I put in the number 5, it'll double it and give me the number 10. And this would be the same for other numbers as well. In many real-world cases, the input and output have meanings. Just imagine the subscribe button that hopefully you've all pressed by now. The input would be you clicking subscribe, and the output would be weekly videos on the beauty of mathematics and STEM on your timeline. Another more mathematical function could be the wages that you earn from a part-time job. Let's suppose you earn £10 per hour. The input of the function could be the number of hours you work, and the output could be the number of money you earn. So if you work for 1 hour, you'll earn £10. If you work for 2 hours, you'll earn 20. If you work 5 hours, then you'll earn 50, and so on. Now already, without using any complicated calculus, there's something really important hiding here. The output changes when the input changes, and that simple idea is the seed that grows into calculus. And I find it remarkably beautiful. We've seen this basic idea of a function, but what does this look like mathematically? Well, we can say that for every hour of work, we multiply this by £10 to get the total payment. So we could define a function f, where we take some input x, so in our case, x would be the number of hours worked, and we'd write the function like this. And then this function would equal the value that we're trying to compute. So for us, we're trying to compute the total payment. So to calculate this, we'd simply multiply our x value, the hours worked, by 10. So the full expression would look like this. F of x equals 10x, where x here is the number of hours worked, and f of x is the money earned. This is, of course, the general definition, but what about if we want to evaluate it at a certain x value? We have this function, but how do we actually use it? Well, if we know that we've worked 1 hour, then we'd write f of x equals 1, so we're inputting the value x equals 1 into here. We can also write this as just f of 1, and this would equal 10 times x, where our x value here is 1, so this would be 10 times 1, which equals 10. And we can do the same for any other number of hours worked, so let's say 5. If we input x equals 5 in here, we end up with this expression, and we find that the function equals 50. So we can say here that the money that we've earned from 5 hours of work is £50. Lovely stuff. Of course, everything we've done so far has just looked at numbers, but the really beautiful thing about functions is that we can plot them on graphs, and we can show what their behaviour looks like. So the horizontal axis would represent the input, in our case, hours worked, and the vertical axis would represent the output, in this case, money earned. So the horizontal axis would have the label x for the hours worked, and the vertical axis would be labelled f of x, in this case, money earned. If you've seen functions or graphs before, then you might know that f of x here is sometimes denoted by y. So the point 110, which is denoted like this, means that after 1 hour, you've earned £10. The point 220 means after 2 hours, you've earned £20, and the point 550 means after 5 hours, you've earned £50. Of course, if we keep adding more and more values, these points will form a straight line. And the reason it's a straight line is that the relationship is steady. Every extra hour adds exactly £10. The output increases by the same amount every time. That's what makes this graph so simple. Its steepness never changes, so for every 1 step to the right, the graph goes up 10 steps. Now this steepness here is called the slope. In this case, the slope is 10, and we compute this by saying the change in the f direction, which is 10, divided by the change in the x direction, which is 1, and this gives us the number 10. And this matches the real world meaning. You earn £10 per hour, so here the slope tells us the rate of change. It tells us how fast money changes as hours change. But not every function is this simple. Many things in the real world don't change at a constant rate. Imagine a car starting at a traffic light. At the exact moment the light turns green, the car starts from rest. At first it moves slowly and then it speeds up. Then it covers more and more distance each second until it hits the speed limit. To keep the math simple, we can describe the car's distance from the traffic light with this function right here. F of t equals t squared, where t is the time in seconds, and f of t is the car's distance from the traffic light in meters. We can plug in values here to see what's happening. So at t equals 1, we'd have f of 1, which is just 1 squared, which equals 1. So the car is 1 metre away after 1 second. After 2 seconds, we'd have f of 2 equals 2 squared equals 4. So the car is 4 metres away after 2 seconds. And similarly, we can look at 4 seconds. So f of 4 is 4 squared, which equals 16. So the car is 16 metres away after 4 seconds. Okay, so we can clearly see the graph here, but how do we compute the slope for this graph? For a straight line, there was one answer, but for this curve, the slope depends on where we are. Near the beginning, the graph is quite flat, but later on, the graph is much steeper. So now we need a more precise question. Not what is the slope of this whole graph, but what is the slope at this exact moment? That question is asking for the derivative. The derivative tells us how fast the distance is changing at one exact moment, or visually, it tells us the slope of the curve at one exact point. And derivatives are how we measure that changing slope. To build up the idea of a derivative, let's first focus on one point on this curve. So at t equals 3, that is at 3 seconds, the car is 9 metres away from the traffic light. So the point on the graph is t equals 3 and f of t equals 9. Now imagine we want to know how steep the curve is exactly here. The problem is that slope usually requires 2 points. For a straight line, we'd pick 2 points and ask how much did the output change, how much did the input change? Then we'd simply divide. So the slope would be the vertical change divided by the horizontal change. This is often denoted as dy by dx, or in our case, this would be df of t divided by dt. But if we want the slope at one single point, we have a problem. One point by itself does not give us a change in the vertical or horizontal axis, so we need 2 points to calculate that slope. So here's the clever idea. Instead of trying to find the slope at one point immediately, we start by choosing a second point nearby. So let's take t equals 4, where we know the function at t equals 4 is 16. At t equals 3, the car is 9 metres away. At t equals 4, the car is 16 metres away. So between 3 and 4 seconds, the average speed is the difference in the f values divided by the difference in the t values. So here this would be 16 minus 9, all divided by 4 minus 3. And this gives us the value 7. So between 3 and 4 seconds, the car's average speed was 7 metres per second. This straight line between 2 points on a curve is called the secant or secant line. Its slope tells us the average rate of change between those 2 points. But remember, we don't want the average speed between 3 and 4 seconds, we want the speed exactly at 3 seconds. So what do? We move the point closer. So let's look at 3 seconds and 3.5 seconds. The average speed over that smaller interval gives us a better estimate of the speed at exactly 3 seconds. Let's move it closer again, so between 3 and 3.1. This time interval is now even smaller. But let's move it even closer again, between 3 and 3.01. As the second point gets closer and closer to the first point, the second line starts to settle into one particular direction, and eventually it becomes almost indistinguishable from a line that just touches the curve at that point. This line is called the tangent line. And there we have just discovered the instantaneous rate of change at a given point. Now this idea is crucial in differential calculus, and it's known as a derivative. Formally, we would say that the derivative of f at the point t is the slope of the tangent line to f at the point t. But how do we denote a derivative? Well, one way is Leibniz notation, where we'd have the slope equals df divided by dt, or more generally dy by dx for an xy graph. This notation refers to really small changes in f divided by super small changes in t, like we've already seen. Another notation is f prime of t1, where t1 is a point on the graph. So you might also see this in some mathematics textbooks or lessons online. It really depends on how people like to format their derivatives. Now, everything we've touched on so far has been written down so that you understand the reason behind the formal definition of a derivative. This is the definition that you'll see in most textbooks, and it was one of the first things I learned at university. Now, when I was in A-levels, I learned the general rule of thumb for a derivative. If you have some general expression like ax to the power n, then the derivative would just be n times by a times by x to the power n minus 1. So you times by the power and then you drop 1 to the power. But I was never really taught explicitly where that came from. And that's what we're going to understand now. Now, as a reminder of what we've just covered, when you have some slope of a function and you want to calculate the derivative at a point, so df of dx at x equals 1, for example, then we would take that point, x equals 1, and nudge the point some small part away. We'd call this dx. Then we'd look at the resulting change to the output, df. The derivative is whatever the change in f divided by the change in x approaches as this dx approaches 0. Now, notice that if we stick with the original f of 1, the point that we want to calculate the derivative at, then nudge it by some dx value, we'd have this general expression here, where we'd have df divided by dx equals f of 1 plus dx minus f of 1 all divided by dx. That's simply the equation for the slope. And we want to find out what this ratio approaches as dx approaches 0. Remember, when we're trying to get the instantaneous rate of change at a specific point. To do this, all we do is add a lim notation at the front with a dx arrow 0 below it. This is known as a limit, and this will be the second topic in this series, so make sure to subscribe. Now, what this means is we're asking what happens to the limit of this expression here as dx tends towards 0. And what we've just uncovered is the formal definition of a derivative. But actually, in formal definition, this dx here is replaced by the notation h. Now, there's some speculation around why the letter h is used here. There are some papers that actually used I in very early mathematical history for increment, so I meaning increment, but this was presumed to have been changed to avoid confusion in notation, of course, with imaginary numbers. Other people have said that it's perhaps because f and g were used as functions and I was used as imaginary numbers, so the only letter left was h. But anyway, this gives us this formal definition of a derivative right here. So we can simply choose any point on our curve, so an x value, and use the right-hand side to evaluate the derivative at that point. And this is really, really beautiful mathematics. Now, let's do it for an example so you can understand how this works. I'm going to be showing you a solution to a specific example with derivatives using a platform called Vieta Space. And the reason I'm doing this is because it's so handy, I can simply screenshot the function that I want to put in some sort of LaTeX notation and it'll write it out exactly for me. So let's start with a definition of a derivative, which is what we have here, and we've already discovered this in our video. The next question is, well, what function should we choose? I'm deciding to go with the previous example that we had, which was f of t equals t squared. Now, I've chosen this for two reasons. One, because we've already seen the expression and we've already discovered it in the video, but also because you might know that t squared or x squared is the classic example that you start with when learning derivatives. If you've done lessons on this before, you might recall that you simply just times by the power, so this would be 2, and then drop a power, so 2 minus 1 would be 1. So if you calculated the derivative of t squared, you'd just get 2t. Now, that is true, and that is what we are taught in classrooms, but when you go on to university, you can understand why this is actually the case and why we get that value for the derivative, and that's what I'm going to show you with this example. Now, I could write out this entire expression for a derivative again, but the really nice thing with Vieta Space is that I can simply screenshot the previous function that we had and then use its AI feature to ask it to change the x values for t values, because we're using a coordinate system based in t, not x here. So this is what we're going to solve here, but interestingly, we're not going to put in any specific value of t, we're going to try and solve it explicitly. So see if we can get a general expression for the derivative. So the first thing that we're going to do is we see this top half that says f of t plus h minus f of t, and we can expand that out. So let's do so. So if we start with just f of t plus h and input t plus h into our function, this would be t plus h all squared, which equals t squared plus 2th plus h squared. We can start by substituting this in. So again, I'm just going to screenshot our derivative and paste the screenshot in so we don't have to mess around too much. And I'm going to use the AI feature again to ask Vieta Space to basically change the f of t plus h here with what we've just calculated. Now, the reason I'm showing you this tool here is because it's really handy for me to speed up mathematical writing and basically focus on doing more of the problem solving than the writing aspect. So I really like Vieta Space for this. So the derivative has become this. We now can simply substitute what our f of t value is in here because we know that f of t equals t squared. And again, I'm just asking Vieta to swap that. Again, I could have done this, but I like to highlight the really cool features that Vieta Space has on here as well. We now have this form for the derivative, and we can clearly see that the t squared terms here must cancel, so this gives us this expression for the derivative right here. You might notice that we can factorise the top half of this expression, so we can take out a factor of h. So this would give us that 2th plus h squared is simply h, open bracket, 2t plus h, which gives us this expression for the derivative. Now you might also notice that we can cancel out the h value here. So we have a h value on both the numerator and denominator, and so this h value can cancel out. So the h's cancel, and I'm going to write out this expression in Vieta space to stop showing you so much of the AI features and show you that you can actually write if you just want to write yourself. So here I'm writing out the general expression and swapping out the limits here, the general expression for our new function. So we have df by dt is simply the limit as h tends towards 0 of 2t plus h. Now this expression for the limit, we can really see what actually happens here. So we have h, and if you obviously have h tending towards 0, then h is going to become 0 in this case. So this derivative we would now have as df by dt simply equals 2t, because as we're tending h towards 0, h is obviously becoming closer and closer to 0, it's therefore 0, and so our definition for derivative for this specific example is df by dt equals 2t. So if you ever wondered where you get the general expression for x squared or t squared when you calculate the derivative, this is exactly how you do it. Now if you want to check out Vieta Space, which is the platform that I've just used to calculate all of this and what I've shown on screen, then I've put a link in the pinned comment and in the description, so make sure you go check it out. We've just seen the formal way of calculating the derivative of t squared equals 2t. Now, all we need to do if we want to calculate the rate of change of our car at any time is to plug in some times into this new expression. So df by dt at t equals 1 is simply 2 times t, which is 2 times 1, which equals 2. And there we have it. We've just calculated the derivative of this function of our car at a specific time. How wonderful is that? This has been such a fun video to make, so if you're interested in more, then make sure to subscribe, and I'm releasing a second video in this series on limits, which will be really exciting, so make sure you subscribe for that as well. And thank you so much to all of my members on this channel who help support this channel even further and make these videos possible. Thank you so much to you and for all the support that I receive. Thank you so much for watching, and I'll see you all in the next one.